All right, let's get started. Welcome to the March 2020 OpenZFS leadership meeting. We have a few things on the agenda for today, and then we'll probably have some time for additional topics or free-form discussion at the end. So I thought I'd start off just by mentioning that we did move the ZOL/FreeBSD repo over to the OpenZFS GitHub organization. So far, I haven't heard of any fallout from that, so that's great. Any questions or updates from other folks on that?
I continue to be confused about what repo I should be checking out.
So if you're working on FreeBSD or Linux, then you can continue using the same URL that you've been using before, the github.com/ZFS on Linux/ZFS, which now redirects to github.com/OpenZFS/ZFS.
So GitHub should have put in place redirects for all of the previous links on the ZFS on Linux GitHub page, so they'll all redirect to the OpenZFS tracker. That's for pull request, issues, comments, all that stuff should get redirected. But you shouldn't have to change anything locally. GitHub provides some instructions if you want to update your remotes.
One consequence of this that I noticed that didn't update automatically with the redirects is the code coverage links still point to ZFS on Linux, which means they don't resolve.
Okay, I will look into that. Yeah,
I'll probably fix itself for any new pull requests, but I think any pull requests that were open during the transition will be confused.
That's links on the Coverity, or whatever it is, application itself, right?
Yeah, that's right.
Okay.
Cool, thanks for mentioning that. Other questions or comments? All right, then I think this kind of flows naturally into the next topic, which was progress update on FreeBSD. Who would like to give an update on that?
I can talk about it a little bit if we don't have anybody from the FreeBSD side here who wants to speak on it.
Yeah, why don't you go ahead? I don't see any of those folks on the participant list.
Okay, just a quick update then. So over the last few weeks, we've been systematically getting all of the test shape for the test suite and getting them running on FreeBSD and Linux. And most of that work has been wrapped up at this point. So there's one big pull request still outstanding that adds the rest of the FreeBSD code into the tree, and that's getting close to ready to merge. Last I heard, they just wanted to make sure that all the tests were passing in FreeBSD, or at least the majority of them, or they understood why ones weren't passing. So the hope is to be able to go ahead and merge the rest of that code relatively soon, maybe this week or next week. Things should be in pretty good shape.
Cool, so that's the remaining PR. Is that only adding new files and not changing any of the existing ones then? Maybe beside files or whatever?
Yeah,
okay.
That was the intent. So we got pretty much everything refactored in the code tree, and the remaining PR just drops in like new directories with the FreeBSD implementation.
Cool. And what do we expect as far as like code review on that? Is that like already been reviewed by FreeBSD folks and we don't really need any more eyes, or do we need more people to look at that code?
My understanding it's been reviewed by FreeBSD folks, and a lot of it is taken from the existing FreeBSD implementation where needed. Right? So there's the common code, and then where FreeBSD needed to diverge, the existing code from FreeBSD was pulled in and updated as needed. More reviewers are always welcome, so if anybody wants to look at that, that would be great.
Cool. All right, but it sounds like unless we hear from somebody else, you're not waiting for any reviewers.
No.
Gotcha.
It's also possible that at least initially when it goes in, we won't turn on the CI by default for it until we're sure that it's passing. So you might have to initially request CI runs, but I hopefully once everything's in good shape, we'll just have that be the default.
So that'll be in the master branch of the single repo then, and it will eventually make its way into the next release.
Yes, that's the plan.
Cool.
Note that this is completely different from FreeBSD integrating it into their system.
Understood.
Yeah.
Just from the perspective of like, if we're going to go and look at doing the
Yeah,
same
no, I
thing.
want it all to be in one repo too. I'm waiting for that.
Yeah, like if we're going to do the same thing, I think we were just waiting for the dust to settle on this one before going and looking at an Illumos approach in the common repo as well. So it's good to know that that's nearly done.
Cool. Yeah, I think we probably need to get the FreeBSD folks specifically to comment on their release process and when it would fit in. But I think the idea is once this integrates into the common repo, then you'll be able to, like, git pull that from GitHub on FreeBSD, make install, and then you'll be running the bits from the common repo.
Yeah, that's my understanding as well. And there's some documentation out there for how to build it, the out of tree version, if you want to test it on FreeBSD.
Cool. More questions or comments about FreeBSD or repo stuff? All right, we're zooming right through the agenda, but the next one's a big one. So I asked Mark maybe to come and talk a little bit about the DirectIO pull request that's out there, and talk about, well, so I understand that do I understand correctly that you implemented most of this code originally, and then
Brian Atkinson.
Brian Atkinson is working on upstreaming it?
Yeah, so it's a kind of a history there is that it was actually kind of developed in a group meeting with, and Brian actually was there as well, Brian Atkinson, Brian Bellendorf, and a few other folks. And we did a first sort of DirectIO code path and sort of verified that things seem to be working. So a little bit of background here, this is, I work for Cray, and Cray was very interested in achieving some performance improvements with ZFS on NVMe hardware. What we were seeing was that in our performance analysis was that ZFS would drive a small number of NVMe drives to, near their hardware performance levels, but as you ramped up the number of drives, the performance didn't ramp with it. It would ramp, but not at the same rate. And so, with 2, 3, 4 drives, you get near hardware speed, but past that, it began to fall off. By the time you got to 10, 12 drives, you were running at about a third of the hardware speed. This is on tests which are designed to push I/O bandwidth. So these were bandwidth tests, large block reads and writes.
Gotcha.
So after doing some analysis, we discovered that there was some bottlenecks, and one of the clear bottlenecks was the memory management, and specifically the process of copying data in and out of kernel was an issue, as well as some of the other memory copies that were happening inside ZFS.
And then, just so I understand, your use case is like you have a userland application that's doing read and write system calls, as opposed to like NFS or Lustre or something else?
So our performance benchmarking was done using FIO. So we were just doing simple reads and writes. Obviously, our use case in the long term, the different interface, right? It's lower level. It talks directly to the DMU, and so that that's specific to us. And but there's still some costs involved there, although it avoids the in and out of kernel copy cost, obviously. We were looking at FIO. We were looking at actually the process of moving the data in and out all the way from userland into kernel and out. So we implemented sort of, like I said, a quick and dirty version of DirectIO just to see how that would work. The performance results from that were very promising. With a simple striped configurations, we could push pretty much hardware speed IO rates all the way up to 12 drives configurations, which is what we were testing, what we had in hand.
Is this, were you using any encryption or compression or anything on the pool? Or?
So these tests were just raw, simple data. So there was no compression, no encryption happening.
Okay.
We are interested in both of those, and I'll talk a little bit about that later because it does come into play when you're talking about DirectIO. What does that mean to use compression and encryption, for example?
Right.
But we were doing simple, fastest code path, and the basic implementation was for the read side. Of course, it's pretty straightforward. Read is already pretty much immediate IO path. The main difference in DirectIO read was to avoid doing the copies of the buffer from the userland UIO into an ARC or a debuff and then stash it in the ARC. Instead, pages into memory and essentially read directly into those pages. So there's no memory copies. So we hand those pages all the way down to a block layer, essentially. On the right side, things get a little more complicated, a little more sophisticated, since ZFS is really architected to buffer IOs to obviously to use a pipeline to gather together lots of writes and push them all at once at the end. So the DirectIO implementation there essentially leverages the DMU sync code path, although it's a variation on it. And this is actually, Matt, derived from work that you had done some time ago, sort of an initial implementation of the concept.
Yeah.
And I sort of fleshed it out a bit more. So back to your original question, did I write the code? Most of it I did write. There was definitely contributions. Brian Atkinson is sort of the person I've been relying on to shepherd things upstream into the community. And he has also been contributing to some of the software development as well. And Brian Behlendorf has also contributed now and again to the project as well. So but those largely I'm responsible, I think. We'll take the blame at least for the basic concept based off of your initial design.
Cool. Yeah, I think that speaks a lot to the motivation of what you're trying to achieve with it, which is cool. A kind of side, well, I'll leave my side tangent for later.
Okay.
Yeah. So you talked a bit about the motivation. I wanted to hear. So I want to make sure we covered kind of the implications of directly reading and writing, and then kind of take that and then talk about the user interface,
right?
And kind of how we could simplify it from what was originally proposed. So it sounds like you are mostly concerned with like raw performance of large block sequential-ish IO. So getting rid of the B copy is a huge deal for you.
Right. That was our primary motivation behind it.
Yeah. And the fact that then it doesn't become part of the ARC is kind of like a side effect that it's not really a primary goal, but it's fine for you.
Right. And as it turns out, again, in our use case, it's actually somewhat of a benefit for our use case and in general for high bandwidth use cases like this. where you can obviously see this being used in a Lester environment is this is when you want to push a checkpoint down to disk as quickly as possible, for example, and you don't really need that to be cached anywhere, and so you don't want it necessarily to be cached. So the fact that it isn't going into the cache is not an issue, and the fact that we're layered with Lester also means that a lot of for the object storage, the caching isn't that important to us, and so the fact we're not caching is somewhat of a bonus because it means we can configure the storage to be less needful of cache and allows us to say, all right, we don't need a lot of memory really because we're going direct IO.
Yeah, but we do have the existing like primary cache property that lets you choose whether like a particular data set is cached in the ARC. So like the big kind of new value add for your use case is the performance improvement of less copying.
Correct.
Yeah, gotcha. So I took some notes in the, or I added some notes before the meeting into the agenda document if folks want to follow along, just to kind of structure the conversation, because I think it's a little bit tricky and there's a lot of related things. So I was also curious from hearing from other folks who might want to use direct IO in terms of what their motivations are. So we talked about like, copying stuff less. There's also less memory being allocated, even temporarily. Like we don't have to keep dirty data in the debuff cache. The data is not added to the ARC cache, which is not really unique to this, but it's one of the semantics. And then the writes happen before the call returns, but the data is not necessarily persistent unless you're additionally doing a sync, right? So all these kind of combined in the current implementation of like you're doing a direct IO, you're requesting direct IO and you're doing a direct IO write or read, you get these semantics. I think one of the things that we need to figure out for the user interface is like what different modes do we make available? And one of the key things is like, how do we treat partial block reads and partial block writes? Right. And that's where I think it would be helpful to understand like which of these like implications is really key to the behavior. And so we would want to preserve with partial block accesses and which of them are kind of ancillary.
Right.
If it makes sense. So to give an example, like if everybody agrees that the point of direct IO is that it's a go fast mode, then if you're doing partial block writes, if you do those directly, then the performance might be much, much worse.
Right.
Than if we did it the old way. So we might say, oh, like you did go fast mode, but I noticed that you're doing a sub block write, so I'm actually gonna cache it and go through the whole normal write code path.
Having been punched in the face repeatedly by the read modify write behavior, even in the not ostensibly go fast path, like it's kind of like, it's like when a SQL database will do an unindexed query for you, which is like fast for a while until it's not, and then it's just really awful.
Yeah.
And there's no, but it's like, it's because it's magical and it's doing the extra work or the slow thing on your behalf, and there's no like direct feedback. The transition from fine to awful can be a big surprise, and it can be too late to deal with it if it's not explicit and upfront, I think.
I totally agree, and I think we should definitely consider making the semantic be like partial block writes equals partial block direct IO writes just fail, and the application has to go back and either change their request size or not request direct IO explicitly.
Is that true of existing direct IO support in other file systems generally? Because I mean, there's a bunch of direct IO specific stuff that you've already got to deal with, right?
So typically, direct IO semantics are notoriously squishy, and so the typical expectation is that as long as you are page aligned, things will generally work. But I think it's up to, and in fact, it's usually stated in the documentation, it's up to the file system to choose some more of the specific semantics. And so I think you may want a mode, certainly, and perhaps the default is, as Matt suggests, that it fail on an unaligned IO, it's non-block aligned. But maybe you also have a mode that's compatibility that says, well, yes, you will not actually fail, but will fall back to another mode that says, we'll actually do what you ask and do the poor performing read, modify, write on the fly for you. I don't know. That's part why we're having this discussion, I suppose.
I do have one quick follow-up question with the talking about reducing the number of copies for writes. Is it reducing it to 0 a goal, or is it reducing it to 1 copy? Because I don't really like, what do you put in the checksum if the user process can still like change the data on the way in? I guess in the 0 copy case seems like it would be difficult to do.
It's a good question. And so, you know, the way you usually support it, well, it's currently implemented in the code, is that it is 0 copy. The checksum is computed on the fly because the checksum, the IO is actually written as part of the IO call. You can sort of have the expectation that no modifications are going to be made to that block while the write is in flight. And so therefore it's simply mapped and computed and written all using the mapped pages. And so there's no extra protection of copying the data aside before you compute the checksum. So yes, if the user was to modify those pages while the IO is in progress, you could end up with a checksum error.
So would that would be visible to scrub, right?
Yes, you'd end up with a checksum error.
Yeah, I think this is the normal expectation for DirectI2 on most file systems. Like, while the pages are in flight and you're in the system call, like, no user space process should touch that mapped memory for the duration of the system call. I don't think that's too abnormal for applications to deal with.
I think that makes sense for applications, but like if it starts to show up like how do I tell the difference between an IO, like subsequently I'm an administrator of a system, I don't really understand anything about DirectIO, and I do a scrub of my pool and it reports a bunch of checksum errors. How do I tell the difference between checksum errors from shenanigans and checksum errors that are legitimate?
So wait a minute. So are you implying that a scrub while DirectIO is in progress might generate checksum errors?
Well, I mean, my point is, I think like if I'm doing a DirectIO write, and then in another thread I futz with the buffer underneath while that's happening, so the checksum is inconsistent with the data that is written, and then I don't read it for like a month or whatever. Like I'm not gonna see that until someone tries to read or scrub the data, right? Is that not true?
Correct. Correct.
That seems like a big problem to me.
Yeah, I don't think you'd be able to tell them apart at the moment. You're right. It would just look like corruption.
And I mean, effectively, from the end user's point of view, they would see, like, I did a DirectIO write. You said you wrote the data, and then I can't read it because it gets checksum.
Right, or you get right.
Right.
Yeah, I mean the alternative, like, I mean, if they did modify it in flight, though, they're going to get corrupt data anyway, right? Because they modified the block while it was being written to disk in user space, and they're going to get garbage back.
They're going to get they're going to get blocks. They're going to get what it was at some point in time.
It might not be consistent, but the storage layer of the system will at least be able to return what it wrote to disk correctly, even if that data is not meaningful to the application because it was silly.
I mean, that's true of a write we call today, just a normal non-DirectIO write. Like, if the userland can be doing stores into that memory, and like we're going to write some version of it from some point in time, and store the checksum of what we wrote.
Right.
Yeah.
Right. So your concern here is that the checksum error, in general, you assume a checksum error implies media problems or perhaps some latent bug in the code, of course.
I mean, today it does imply those things. Like there's generally no other way that a checksum error would arise, I think.
Yeah.
Well, checksum errors can arise from media or data path. I mean, it doesn't have to be the media itself. Could be some part. It could be RAM. Could be
but it's
HBAs. Could be.
It's a hardware problem.
It's a component or a software fault
well-
rather than an application being able to influence directly that behavior.
Correct. That's correct.
Everything is going to assume that if you get a checksum error, there is something wrong with your pool.
Right, and it could. I mean, from a fault management perspective, like if the system that you have for doing fault analysis is like, you know what, that's 10,000 checksum errors, I'm going to spare out the disk. Like, I mean, is not necessarily an unreasonable posture. So, like, perhaps at the very minimum, we need to write some kind of flag for a DirectIO written block to say that the checksum might not be indicative of a hardware fault, perhaps. Or at least it's a different class of checksum error from the previous kind, perhaps.
Yeah. Would it be possible to change the memory mapping, like to change the, I mean, maybe this would destroy performance, but
It's
like,
too expensive. You have to do TLB flushes across all your CPUs to remove the right
Yeah.
thing. And at that point, you may as well copy the block generally, unless it's a huge block.
right? I mean, it probably is huge. Like in your cases, it's probably 16 megs.
Yeah.
Maximum block size, which it might work, but then it becomes a very, very niche use case.
Yeah. No, I think I kind of, you know, if this is you know, I think it's to market as some sort of direct IO write that says, okay, these are soft.
Yeah, like maybe the checksum algorithm has a new bit in it that says like, oh yeah, it was checksummed with this algorithm, but but like with potential of userland shenanigans.
Right, exactly. So that we sort of mark it that way. And that way, then you can make a decision later. It's like, okay, I got a lot of these errors, but they're all checksum based blocks. And so I can make as an administrator a decision about how I want to treat those differently than some other checksum errors I might get.
Would you then allow the application to read the blocks that were inconsistent with the checksum? Because today you effectively get an error, right? You can't really see through and get the data that is on the disk, even if it's not matching the checksum.
What would be the
point of the checksum at all?
Yeah, well, what would be the rationale there to say, well, I want you to read it regardless of whether the checksum is correct?
Yeah. So Lustre struggles with a similar problem when it sends buffers over the network. Its solution to it was to check some before and after the buffer was sent, because they're directly mapped, they might be modified. Maybe we could do something similar. Could we check the checksum after we've written the pages, relatively inexpensively?
But what if you change the data and then change it back between
well, you could at least fail the I/O maybe. I mean, worst case, if the checksums differ, just turn an IO error. You don't want to checksum it again, but at least you would know at right time, right?
But my point is, like, if it's a 16 meg record, right, there's probably going to be long enough during the processing of that IO for me to, it gets checksum once up front, and then I change it a little bit while you're like copying it into the storage device, or the storage device is doing DMA, and then like I've timed it such that at the end I put it back. So you checksum it again, and it checksums the same as it did to begin with.
Yeah, I don't know how to deal with that.
So is the point here you're trying to protect against someone who's intentionally and maliciously trying to generate?
I mean, I think it is worth considering the security implications of a feature like this, right? Where you're exposing a new level of control over the kernel interiors to user space, basically.
Yeah,
Which
I mean,
maybe that's fine, but like I think it's worth being explicit when we do it. Like,
yeah, I think the concept of saying this is, you know, a special type of checksum or a special type of write that has these, it's open to these, this particular attack vector, let's call it, says, all right, we can decide what to do with it. Then you can build other infrastructure if required, but doesn't preclude the ability of users to leverage this facility. So you say, all right, we can treat these blocks as in a different fashion.
Yeah, from a security point of view, I think that if we went down that road of continuing to let them get the false checksum error, if applications could generate the false checksum error, then I think that we can't make the default be to honor direct IO rights, right? The default has to be that you cannot cause us to get checksum errors, and you have the system administrator has to go and do ZFS set direct IO rights equals enabled or whatever, something like that.
You could service reads by default, just not
Yeah,
writes, I think, and without the option.
I agree.
Would suppressing the checksums be sufficient? Because this is an issue that any file system that implements DirectIO has, right? They just don't notice because they don't do checksums. They'll just happily return whatever was written.
Yeah, basically
So,
saying like, oh, you did a DirectIO write, therefore that implies checksums equals off.
Yeah, I mean, in an extent-based file system, I think the contract is fundamentally different too, right? Like you just, I put something on the disk, you put it in the place where you promise you're always going to put it, and then you give it back, and it could be wrong.
I mean, we could still generate checksums and just suppress them, perhaps. Not count them as failures. They differ, but
and that's what we're talking about, I think, with a different sort of checksum mode, which says these are soft checksums, or these are direct IO checksums, and therefore they're treated differently.
Absent checksums, what happens with mirroring? Like, how do you know which block is the good block?
In ZFS, in general, if you turn checksums off?
Specifically in ZFS, right? The checksum forms a part of the process for determining whether a mirror read from half of the mirror is okay or not, right?
You'll never determine it's not okay if you don't have a checksum to compare it against.
Right. So
you get different versions though too, right? It's totally possible we'd end up with different versions in both halves of the mirror. And
so then how would you reconcile, like assuming I always read from both sides of the mirror, which side do I give to the user in that case?
It would just be random.
Mm-hmm.
Yeah.
Okay. I mean, so to be clear, like I fully support the idea of a go faster mode. I just think it's important that we consider what other parts of the stack not being able to necessarily depend on the checksums working will affect. That's all, I think.
Well, I mean, I think really the issue you raised is that we'll get a false checksum error.
No, it'd be a true checksum error.
Here. Sorry, you're right. It's a true checksum error, right? But what I'm saying is it doesn't imply a hardware issue which you normally attribute a checksum to. That's really the only issue we have here. I mean, still, if you fail to checksum, all the other aspects of the code stack seem relevant. It is a checksum error.
I mean, also for mirror writes, there's probably not a way to atomically issue the 2 or the 3 write IOs to different devices. Like, let's say, because you're effectively mapping that user buffer, and you're going to have probably maybe as many as 3 different HBAs do their own DMA activity to get those bytes into the storage. They're not going to do it necessarily at the same point in time, and they might not see the same values either.
Yeah, I mean, you would have this similar kind of problems with RAID Z as well, where like the parity information would not be self-consistent.
Yep.
So maybe for now, why don't we table this and kind of leave it to the implementers to come back with a proposal of how you want to handle this, which might involve, multiple passes or some new checksum mode or whatever, and then, document like what the proposed semantics are and what the implications are, and then we can, continue the discussion on this, on the PR or at the next meeting. Does that sound reasonable?
Definitely.
Yeah.
Cool, thanks. So should we move the discussion to the user interface a bit? One of the things I wanted to get input on from other folks that might have experience using DirectIO on other systems is what the expected semantics are, like in terms of caching and how it works with subblock writes especially. So I wrote some notes kind of in the design, in the meeting notes. So I think that we need some kind of mode where like, it's the same as the current behavior, right? We just, you request direct IO, we ignore that, we do it the old way. Just so that people can have compatibility with the old ZFS behavior. And we want some new mode that would be the new default, which does, in at least some cases, do direct IO requested operations directly. And then maybe we also want some mode that's like, does some IOs directly even when you didn't request it. If you want, if it's like, I know that it would be better to do it this way, but the application doesn't know to do the direct IO requests. But we need to figure out, and the key things to figure out are kind of what exactly, like I said, there were a lot of wiggle words there, like some IOs will be performed directly, and which ones exactly we're talking about. And a lot of that comes down to the partial block reads and writes.
Mm-hmm.
Yeah.
So
Fail those.
So it sounds like, Sean, you're saying we should fail those?
Yes, if you're trying to, the thing is, if you're doing direct IO, you're generally not doing something as a very generic application. You have a very specific need, a very specific environment in mind. So yeah, you need to know the block size that is going to be used. And you don't do the direct IO unless it is going to be that block size. If you try otherwise, fail.
I would agree, at least potentially on the right side. Not so clear to me that on the read side, that's necessarily the right semantic. I think there's still a lot to be gained from supporting partial read direct IOs.
And Mark, what's the use case where you're thinking about that? Like, I agree in the abstract that like it doesn't degrade, like it doesn't make things that much worse because you're doing a partial block read. Like we can still do, we can still avoid a lot of B copies and whatnot.
Right.
I'm curious about what like.
And so explicitly, I just think that it's not uncommon that you want to do, in a database application, for example. We used to see this at Oracle a lot, where customers wanted to be able to do a database scan rapidly, so they wanted a relatively large block size for their database, but at the same time they wanted to have an efficient read access to it, and so they're interested in a direct IO, small block read for 8K, 4K reads that they want to perform along the way. And so it seems to me that you could get some performance out of it, direct IO, by saying, sure, you can just still do those, and we won't cache your extra IOs, particularly in a database example where it's random IO and you don't really need, you're not doing sequential stuff, so the caching doesn't really give you anything.
Yeah, I think the key aspect of that workload is that reducing the B copies helps your performance more than caching would.
Right. And so there is, and obviously this is a decision anybody makes with direct IO is whether that's the win or not, because the alternative to that I can offer, the counter to that, is that actually if your working set is small enough, then you'll pay a price for a little bit slower reads for a period of time, but once it's all cached, now you're getting things faster because you're pulling it from cache all the time. But that's an application specific or a context specific decision.
You're effectively always taking responsibility for your own caching, whether you do it or not, basically, right?
Like if you're doing direct IO.
Yeah.
Yeah.
In the direct IO case, either you're going to cache it yourself or you don't care that it's uncached.
Right.
Yeah.
Yeah, so I think if that's kind of one of the underlying assumptions or like semantics of direct IO is like, it's not caching stuff, then I think that's kind of one more point in favor of just say no to partial block direct IO. I love this idea because the implementation is simpler.
Agreed.
I know that in a lot of other file systems, you can do direct IO, the block size is effectively 4K. So like your reads and writes only have to be page aligned to get the direct IO behavior. With ZFS, like the default is record size 128K. So in the default case, you might have a naive application that's like, oh, I'm going to do DirectIO with my 4K aligned chunks because that's what DirectIO means. And I'm on ZFS and I have a naive system in that just did ZFS create whatever, and they're using the defaults. And we have record size 128K, but they're requesting DirectIO at a 4K level. I kind of feel like failing in that case.
It really,
sense.
I mean,
But
again, a pretty extensive experience with accidentally not realizing that the write size and the record size were mismatched, and then having to deal with it once the database is a terabyte in size. Like, it feels better to fail it up front, I think.
does anybody want to make a counter? Like, I think that's great. Does anybody want to make a counter argument that we should not be failing these? Let's put it this way. Should there be any mode in ZFS where we would not fail misaligned DirectIO reads, except for maybe like the preservable behavior where we're just always ignoring DirectIO all the time and always going through the arc?
Or turn them into just non-cached reads.
Well, I think that's the question. Should we
That's the kind of magic degradation thing again, I think, right?
Yeah.
Like,
Well, it's a little bit of a middle ground, right? It's saying, all right, what I care about the DirectIO semantic is that it's not caching, and it's not so much about the lack of B copy that's an issue for me or something. But as Matt pointed out earlier, you can actually set that in as a property as well, so you can get at the same feature the other way. But it does require you to know what you're doing or know how to do that kind of thing.
Yeah.
in the case that you're not worried about the B copy overhead, is the only other downside of caching that it uses a bunch of memory and that you're thrashing other things out of the cache, conceivably?
And you can address that today with the primary cache property.
Right, but is there some other thing that I'm not thinking of that other than the performance copying overhead of the caching mechanism? If that's not your problem, what is the other problem with caching, I guess? What are the other problems with it?
I have some other problems with it, which are kind of related to my tangent, which I will wait until the end of this to bring up, because it doesn't have to bear on the semantics of this DirectIO thing.
Okay.
Yeah, I think, to your question though, circling around a little bit, Matt, you might want to put out a request sort of to those who are more directly interested in leveraging DirectIO as a feature if they have any issues with this or they have any particular use cases that make sense. I said, from my perspective, I can say, well, yeah, it doesn't matter to me because I have a very constrained environment, and might be some other folks out there who are using or wishing to use DirectIO in different ways who might say, no, it's really important to me that I'd be able to do some sort of partial block chunk at some point. I mean, I agree with you though. I mean, from a code perspective, it would definitely easiest just to fail all of them or default them to non-DirectIO. You didn't meet the semantics, so therefore, or the criteria, so therefore you go non-DirectIO or something like that. But even there, sorry.
I mean, it feels like we could do a phased approach too, right? Because this is a new mode that you're going to turn on the data set,
right?
Which changes the DirectIO posture to be, perhaps in the first version, more strict, but then also faster. But you're not going to break anybody who hasn't turned that mode on, and handling partial writes or whatever is strictly less constraining than not doing it. So I think you could always do that work subsequently if it turned out to be necessary without really affecting the first phase of that work, I think.
Agreed. You could expand your support as time went on potentially.
Yeah, and you can always have, I think we can always make the argument that you did some DirectIO stuff and it failed. Okay, well, just change the property back to ignoring DirectIO and you get the old behavior.
Yeah. So a couple of comments here to give you sort of a context from a coding perspective of how trying to implement some of this stuff. Because I actually tried to have implemented sort of a fully generalized implementation of DirectIO here. And I can tell you that, you know, there is significant complexity in supporting the partial block reads and writes, particularly if you want to be purist about direct partial block write is pretty complicated, and a little bit easier doing the partial block read side. And then also supporting a mixture of direct and non-direct IOs in the same sort of IO stream is also a bit complicated, because you have to do a lot of fiddling behind the back to make sure that things remain consistent between your direct IO data and your non-direct IO data. So sort of defaulting to, you know, old behaviors for non-aligned IO, and then saying, okay, well, gee, you issued 4 reads, and the middle read, 2 reads were aligned. The first and last were unaligned, so now I'm using, you know, a mixture of IO modes there. It is actually relatively complicated to make sure all works properly and does the right thing.
What is the plan for coherence between direct IO and non-direct IO activity on the same file?
So that's a good question. The easy answer is there is no guarantee. The harder answer is you can try to make sure that it's consistent by doing appropriate locking in various places, but it gets complicated.
Is that, so can we drill down on that a little bit? So for reads, the issue is like, we might have done a direct IO write, in which case we need to read that data back in.
Right.
Or more that you might have done, you may have done a regular write, which is sitting in the ARC, not yet flushed to disk. And then I go and do a direct IO read of the same region of the file.
Yeah.
And it goes and does a storage request, like to the HBA or whatever.
The opposite. I think that's a little bit easier to handle, because it's like, you know, you come in with a direct IO read and we're like, oh, I already have the data cached.
Right.
We're not, I'm just going to bcopy it to you instead of doing an IO to disk.
Although,
Yeah.
But you've still
That
got
would
to
be
go.
different
you're
Still
not
got to go.
being purist about your direct IO. Direct IO says, I always go to disk.
Yeah,
Right.
it's not
Yeah.
for sure.
You've still got to take the locks on the cache structure and do a bunch of checking to see if the region exists in memory or not, right? I mean, that's
Yeah.
in if you're going to do the coherent version.
Yeah, although that, yeah. The arguments for direct IO so far have not been related to any of the per block overheads,
Right.
because these use cases are for large blocks, and so, you know, getting the lock on the block is not expensive.
No.
Okay.
So what I've seen from most file systems who implement this is they push all of these problems up to the application. So you're not guaranteed coherency or anything like that. You will bypass the cache. You will get the not cached version, at least for the Linux file systems I'm aware of. So they kind of punt on a lot of these issues and push them up the stack.
From a certain perspective, though, their file system structure allows them to do that, right? Like if I create a file on an extant-based file system, like offset 5 is always going to live generally in the same place once it's been allocated. So you only need to like have done the allocation in advance, and then competing writes can, whichever one happens last wins.
ZFS
in this
is
case,
not
we
well
don't.
suited to this kind of.
Right, because you've got the whole tree structure has to be consistent.
Yeah, I mean, so I would argue pretty strongly that regardless of other how other file systems have implemented direct IO, we should try to make it as coherent of semantic as possible. And you know, if we want to punt on things, then we should punt by failing in those cases.
By saying you can't do direct IO and regular IO to the same file
Like
at the same time.
if you modify the block with a regular write and then you do a direct IO read, direct IO read just fails, right? Rather than letting them see 2 different versions of the data. Like it seems like not that hard to.
From an API perspective, you choose this as a flag at open time, right?
You can choose it as a flag at open time. You can't really do actually, can you request to direct IO on a per IO basis?
Is there a separate direct IO function?
There's an F control for it.
Generally, no.
So it seems like there's a control plane operation where we can make a decision at that time, like you would make the OX goal decision for it, like the exclusive open decision.
Yeah.
Like, I mean, you could say like, I'm not going to let you open a file, the same file for both direct and non-direct I/O at the same time. You could, I mean, you could prohibit that, for instance.
Yeah.
I mean, that sounds reasonable. It is in line with being more strict, right? Failing things that just aren't supported to make it clear.
I'm taking some notes.
I think that one of the chief design goals of ZFS historically has felt like it is about making it so that things either work or they visibly fail.
Yeah.
And this is in pretty stark contrast to a lot of other file systems, particularly. And that like, it would be good to, even if we begin to relax like the constraints around the operation of this thing by making it more complicated and more complete over time, that it would be good if at no point in time we made it wishy-washier.
Right.
And so that you could accidentally do things and have them do the wrong thing and you don't find out till later, I think is the thing that we should really try and avoid if possible.
Yeah, I tend to agree. I think one of the strengths, if once you've written it, is good, you know, that, as much as possible. So.
Hey, Mark, I had a question for you. Have you seen or had to deal with like the case where the alignment is, you know, might be fine at the record size, but not at the sector size?
So, wait, the alignment is good at the block and not sector, or page and not sector, which
Yes.
all of the above.
Yeah. I mean, like it seems like that's another alignment case that I don't know if maybe it's already dealt with, that you know, you're dealing with this when you're actually going to the VDEV and saying, okay, I
Right.
know that I'm at least sector aligned. Or
Well, since our sector size is 4K, it's not been an issue for us, since that's always a page aligned. So it actually is something which Linux wants, is that when you issue a mapped buffer down, that needs to be properly page aligned, or else things get upset lower in the stack. So that's your incoming buffers. In terms of the data alignment, yeah, that sort of gets to all our discussions pretty much block alignment, but yeah,
Yeah.
in theory you could have a block that was smaller than your page or your sector size, and we haven't played with that, so I'm not sure how that's going to play out.
okay.
This becomes increasingly problematic too when you start talking about larger page sizes, which are becoming more and more common.
Yeah.
Right. So that's, you know, 16K or 64K pages still need to be aligned.
Right.
And I'm not how sure that's going to play out with like smaller block sizes in ZFS.
You can declare your buffer, that again from the application layer. You can declare an alignment constraint on the buffer you're using to write your data in, to get to guarantee the alignment there. And then once you get below that at ZFS, it should probably be fine if you have a larger page and a smaller buffer that you're writing out.
Yeah.
Yeah, you're using the pipeline still, right? So when you get down to the VDEV layer.
Yeah.
So
Yep.
maybe like there is sub-block handling there too. That
right.
maybe that just works.
Yeah, I think mostly it does just work as long as you come in with your buffers, that your mapped pages are aligned properly. When it gets to the VDEV layer, the things pretty much just work down there, because it just chops it up and sends it down to the device. So I think that's fine.
Cool.
So another part of this that's kind of problematic from a user interface perspective is there's no real easy way at the moment to get the block size for an application, for a particular file, right? So the application knows. I mean, you can check what the dataset property is set to, but that doesn't necessarily tell you what the block size on the file is.
You can get it in this. by running stat, the stat system console.
I don't think so. I think stats gives you at least the preferred block size. I don't think it gives you the actual block size.
What about
It gives you
VFS
the
stat?
actual block size on Illumos. I'm pretty sure it does on Linux as well.
I know we put that in some structure somewhere.
It's in the struct stat, yeah.
Yeah, there's a custom ioctl where you can get it. But my understanding is that on Linux, it'll return like, you know, say the file's 0 bytes in size still, right? It'll return 128K. It'll return the default property block size. So if you've got, or the file say 4K in size, right, and it hasn't been increased yet, I think it'll still return 128K.
Yeah, that's effectively true.
Right.
I mean,
if you set the record size after a file has begun to be written, does it continue to use the old record size for that file?
If it has multiple blocks, then yes.
Yeah.
Okay, so you need to create a new file after the record size setting has been changed to make it take effect.
Yeah.
Correct.
So, I mean, I'm pretty
So
sure,
whatever it is, it's true for at least the whole file at a time.
yeah. I'm pretty sure that for multi-block files, the struct stat preferred block size is the actual one and true block size for that file. Now, for files that have only one block, you know, we could kind of argue about what does it even mean? What does the block size even mean? You know,
Right.
Yeah.
But yeah, I think that for files with one block, it might be, it's probably returning the record size property rather than the size of the potentially smaller first block, which could potentially confound DirectIO. But like, I mean, come on, like, don't do DirectIO on files that small.
That's right. You're not really gaining much on a single block file.
Well, maybe you are, right? Maybe for some really fast NVMe devices, you really don't want the copy at all. And you want to cut as much out of it as possible. I don't know. Maybe there's a use case there as well. Anyway, I'm just saying that we should have some interface where we can actually reliably get the block size for applications. And if that's stat, that's great. But if we have to change the behavior there to make sure that's true, is that going to cause us any problems?
On Illumos, at least, we use something called SA object size to get to populate the block size field in the stat call, I think, from the look of the code.
Yeah.
I mean, so let's see. What would be the problem that you're bringing up? The problem only applies to single block files. And let's say, you know, you have a file that's, the actual block is 64K, but the struct stat is saying that it's 128, the preferred block size is 128K because that's the property set to that. Then you do a read, like the application does a 128K read, but there's only 64K of data. And so we would have to like jump through some hoops to read the first 64K into the first 64K of their buffer and then zero out the rest of their buffer, right?
Right. I
Yeah,
mean, yeah.
That seems like probably not a huge amount of code to handle that if we wanted to.
I mean, yeah. And what happens now if you reissue? Which interfaces are we talking about going through? Because certainly, if you go through your typical file system interfaces, you'll simply change it down to a smaller block read because it says that data isn't in there.
Yeah.
And if you use map to access, you'll get a SIGBOS if you try to read past the end of the written region.
I mean, it seems like a less than 10 line kind of wrapping function to be like, oh, you want a DirectIO, you tried to read more than the single block that's here, great, like do a DirectIO read of the beginning, passing in the beginning of your buffer, and then D0 the remainder.
Yeah, it sounds handleable. I just wanted to make sure something we thought about.
All right. Cool. Well, we've used up our time for today. I will save my performance related IO tangent to next time. It relates to the per block overheads of doing this stuff. Doing IOs when you have, small record size and you want to read or write a lot of data. There's a lot of per block overheads that I'm trying to address. You might have seen my pull request about ZFS send, like doing arc bypassing ZFS send, which you could also call direct IO, because it doesn't use the arc, it uses ZIOs directly. And I think there's some similarities to what we're doing here with direct IO, but it doesn't really have to come into the discussion of these semantics.
Okay.
So what's the next step on this process?
So I think we're waiting for Mark and Brian Atkinson to come back with some proposals on the problems that we brought up here today, right?
Right. Right. So specifically, I think the main problem was around the checksumming issue. I think I don't know if we've come to any specific conclusions in some of these other places. Would you like a proposal on some of the user interface questions that came up, or?
Yeah, I think at least on the like partial block questions, to like at least post something to the pull request saying that, we had this discussion. The proposal is that, partial block reads will do X, partial block writes will do Y. And, this is kind of how much consensus we got on the call for each of these. And if anybody has problems with these, then let us know. And then if you don't hear,
Okay.
And then change the implementation based on that if you don't hear from anybody.
I think there are three things, right? There's the partial block thing, there's the checksums in flight thing, and then there's the coherence with regular IOs thing.
Right.
Yep.
Yeah.
So same
Be good
with
to
that,
have.
the proposal. And
Okay. Yeah. So we'll put together something along those lines.
Thank you.
Cool. Thanks a lot, Mark.
You're welcome.
Thanks to everyone for staying a couple extra minutes. The next meeting is scheduled for 4 weeks from now. That's the 31st. We could potentially push it out a week so that we're like doing it in the next month.
One meeting per month. Or...
Yeah, rather than one meeting for 4 weeks. I'm fine with just doing.
But it's supposed to be every 4 weeks. Don't confuse me.
All right.
Except during leap years.
Yeah, leap year. All right. I will not confuse you. We'll do it in 4 weeks on the 31st, and it'll be at the earlier time, the 9 o'clock Pacific time.
In the morning?
Yes, 9 o'clock in the morning.
All right. I'm not convinced that time exists.
You can call it from home if you need to. Roll out of bed onto the call.
Just bring your kid to ZFS call day. Or...
Yeah. Cool. Well, thank you, everyone. We'll post the video later, and I'll see you in 4 weeks.
Thank you.
Cool.
Bye.